Hello, my name is Chase Dunaway. I'm a mechanical engineer at New Mexico Tech, currently entering my senior year. And this summer, I was fortunately able to come to CMU under the RISC program. And I have worked on several tasks this summer, all involving safe controls and verifiable safety. And the main talk of this presentation, as well as my poster and my paper that I have submitted in the RISC journal, will be about this topic. So I'll get started. This is the application of real-time safety index adaptation for parameter varying systems. And what do I mean by safety? Well, in the idea of autonomous systems, we want to have some sort of way of verifying safety. And this becomes more important as we start to include autonomous systems into society. So, for example, a drone delivery taking a package and dropping it off. We want to maintain that this system stays safe as we define it, and as I'll get into, while also optimizing computational simplicity and optimality. And then it becomes further complicated by the fact that many systems have varying dynamics, as this drone delivery does. As soon as the package is dropped, its dynamics change, and as well as unknown control bounds for these systems. And so that's the main concept and proposal of this work, is applying a method that is successfully able to adapt to an unsafe system and then make it safe. So for some of the preliminaries, I'll first get into what a control affine dynamical system is. We define a control affine dynamical system as some dynamics equal to some drift dynamics plus some action, which is what we can control. The safety index is a function that measures safety as a scalar value. You can think of it as a Lyapunov-like or an energy function in which we define a system to be safe if it's negative. And so, for example, we can say this car example, we don't want these two cars to collide. And so as long as the car is far enough that it can brake and the distance is not 0 or positive, then we will say that the system is safe. And moving on, we also want to define that the system is optimized such that the safety and the performance are, or safety and is not coming at the cost of extra performance. So we have this minimization constraint which we optimize over. And as a result, we can solve this with a quadratic program in which we just minimize the difference between these two, or the norm of. And in other words, we want this system to be safe, and we want to state that if it's unsafe, that it becomes safe, meaning that if the safety index is positive, we want its derivatives for any state x to be negative. And so in other words, if the system is unsafe, move toward the safe set. And you can think of it like this, where everything below this 0 level set is safe, and that the derivative of everything above the set is negative. This enforces two conditions that we necessitate as safety. First being for invariance, meaning that once inside the set, it will remain inside the set, meaning that it'll be safe for all time. There's always some control input that you can give the system to ensure that it's safe. And over time, or if it is unsafe, that the system will converge back to the safe set. So if the control input is not explicitly in our safety function, then we can derive a new system in which the input is, and I apologize, this should be the derivative thereof. So we can directly enforce the negative constraint we place on the derivative of our safety function. And so with this ensures a relative degree of 1, meaning that if you take the derivative of our safety function, you will see that the control that we have implemented in our control affine system will appear. And so as a result, we can naturally formulate this. And one of the constraints that we have is this k of I value that we need to optimize in order to meet some of the constraints. And we can do that with some of the methods I'll talk about. So this is our main formulation. We want to minimize the cost of the performance over safety while maintaining that the system is safe and that it will become safe if it is not safe. And so I'll get into some of the nonlinear programming that we have for this, in which if the system is unsafe, then there's an infinite number of constraints. But we can solve this system if we use sum of squares programming. And so the idea of this first comes in the concept of creating a refute set, which basically says that if we can prove that the system is safe, then for all x, then we can say that we've met these conditions. However, if we can prove that the system is not safe, or the set that defines the system being unsafe is empty, then it's the same thing as proving that the system is safe. So formulating a sum of squares program, we can use something called the positive stellensatz and formulate this in terms of a local manifold, in which we expand this minimization term. And of course, this is just what we wrote a little bit earlier, where phi, theta, and phi of n are a little bit interchangeable. And this delta term here just represents the choosing either a lower or a higher bound based off the condition of the Lie derivative of your input constraints, or I guess I stated your action dynamics. And so creating a refute set and necessitating that it's empty is what we just talked about. This is the basic formulation of what we said is equal to phi dot. And we can specify that this is negative, meaning that it's safe. If we then flip the sign and state that it's unsafe, but this set is empty, then we can prove that the system is safe. And so for that, we use something called the positive stellensatz. And so positive stellensatz allows us to formulate the problem in terms of a sum of squares, which is a linear combination, and we can then use positive semi-definite programming in order to solve this system. And so we reformulate it as this, where our polynomial is just this p naught, and the matrix Q is what represents the coefficients of this sum of squares. And so the main idea now is to find the thetas and the p of i's that satisfy this constraint. And so we think about that problem being solvable. And one of the main ideas of this is that we have uncertain dynamics in which that there's some sort of adaptation. So we'll also add this tuning parameter rho to our formulation. And then from here, we have a new safety objective, only in terms of the additional term rho, where Q is positive semi-definite. And we use something called Sylvester's criterion to determine positive semi-definite, which in this case will allow us to satisfy our safety criteria. And so with this, we can then apply determinant gradient ascent. And from there, we can basically move smoothly in between various adaptations of the same safety index, meaning that we don't have to resynthesize a safety index, but we can just move between the change in dynamics instead. Okay, so for the application of this, we use a Unitree Go2, which is a quadruped, and we have this basic setup. We are going to alter the dynamics by adding additional weight to the back of this, record its response and fit its kinematics and dynamics. And then we're going to find a failure case in which we're controlling the system either by adding a lot of weight or pushing it to move in a certain way that will cause it to fall over or become unsafe. And then we test this failure case, but now we adapt the safety index accordingly. So whereas in 3, we'll have a safety index, but it's not adapting, in 4, we'll use the determinant gradient ascent method to adapt the safety index as we add weight. So first, we need to understand how the system corresponds to various weights as is. And so for that, we have some control input, which are our accelerations, and we then measure the output state of this. So The dog in practice actually takes velocity commands, but getting the acceleration commands is not too difficult from this. And then as a result, we measure the system's response according to the different weights that we put on to the robot. From the data collected from the motion capture system and the dog's internal sensor feed measurements, we can fit the measured data and our commands to the following kinematics and dynamics. This is just a single order unicycle dynamical system in which we have this basis of these A of F and A of T terms, which are parameters that contain rho, as well as some bias term. And so reformulating this as a sum of squares is what allows us to derive the new dynamics as they pertain to different weights. So A of F and A of G are the varying parameters that I talked about. The formulation of this ideally would be identity matrix for this A of F, and this A of G term would give us this hopefully diagonal term in which we basically weight the control inputs to the response of the system. However, in the most recent formulation, this matrix is more of a free-form matrix, where these bottom 3 by 3 are all free-form parameters, and this gives us the best fit. So with this filtered data, we can then perform a linear regression, in which first we collect the data and then see how it matches the estimated dynamics of the first order unicycle model compared to what we have. And after filtering, we can see that the correspondence between our linear regression increases dramatically, where most of these terms become ratios of 0.9 or above. And as a result, we can calculate the correlation between the physical weight and the resulting A of F and A of G matrices, where we see this correlation grow between A of F, our A of G values, and then the bias terms, depending on how the weight is changed. So we have this linear correlation between the physical weight that we put on the robot and the resulting A of F and A of G matrices, where the objective now is to synthesize the safety index. So we have this function that I described earlier, which is the main objective of what we want to do with the safety index, where if the system is unsafe, we want it to become safe, and then minimize the invasiveness of the safe input compared to a nominal controller. And so the formulation of this system is as such. We only needed to take one first order derivative, or one derivative of the safety index that was prior formulated, in order to make this system have a relative degree of 1, meaning that the control input shows up after you just take 1 degree of this. And so we have to solve for just one k value. With this, we can formulate our system in terms of the Pauli-Stellensatz theorem, where these gammas are our inequalities, and all of these variables represent parts of the dynamics representative of the control that we want. And so we've defined unsafety being a certain area or region within this motion capture room that the quadruped has to avoid. And so we have all of these inequalities that form, and if we can maintain Pauli-Stellensatz, then we can say that the system is safe. So in our formulation, just going quickly, this is the resulting X and Q matrices that we have as they are parameterized. We then find the value of K, and it's K of I if we had more than one relative degree, but in this case it's just 1K through numerical optimization, where we test these control bounds and then see what is the most optimal sum of squares answer. And so as a result of some of our synthesizing, we find this value of K equaling 0.2 roughly. And before we can evaluate the safety index, we must first find a failure case for the system. And so we run the system with a safety index that's non-adapting. And so here's that region that I specified was unsafe. It's this red region. And we can see that the quadruped successfully avoids, and then because the LQR that we're using is a little bit undertuned, it oscillates around the objective. But we can see that this is very clearly safe. However, once we start adding weight, it shifts dramatically. The quadruped itself, we noticed, had difficulty maintaining the weight on its back and carrying its inertia. So if it was moving forward, it would start moving too fast, and then it would basically have to rebalance itself, and almost like an Olympian running the end of a race has to continue past the finish line in order to settle themselves. And so we see this oscillation where it's still safe, but it's on the verge of being unsafe, and the oscillations caused are significantly greater. However, once we've added 5.9 kilograms, we can see that the system is undeniably not safe. So the system first avoids the unsafe region, but then it starts leaning back, trying to fix itself, and then enters the safe region, freaks out a little bit, leaves the safety region, and almost crashes. So at this point, the system is just not safe, even with a non-adapting safety index. And so moving forward, the last thing that we have to do is apply the safety index adaptation method, which unfortunately at the time of these deliverables for RIS was unable to be tested. Hopefully, I believe I can update the paper in the RIS journal or the poster as the results come out, which will hopefully be within the next couple of weeks. Or in the case, there might be a paper on this work. But this is the last step for a very nominal test, or I guess a very introductory test, and then formalizing other tests in which we test this safety index adaptation method is something that we've been thinking about. And so I would first like to acknowledge my mentor, Kai, who helped me out through the summer, basically working alongside me every day this summer, including on weekends. So I'm very grateful for that. And then, of course, Dr. Dolan and Dr. Liu, whose labs I was welcomed into this summer. And then, of course, my appreciation for Rachel and Dr. Dolan for the immense amount of effort they put into RIS and making this a fantastic experience. And at the very end, here are some of the references that I went through. If you would like to see more about this kind of work, then these are some very nice papers that talk about this.